Hey, hello everyone. Good afternoon. Ang pag-uusapan natin ngayong araw ay yung third type ng partial differential equation. So, ang hyperbolic partial differential equation. Ang isang common example ng hyperbolic partial differential equation is a one-dimensional wave equation. And yung form ng wave equation o ng hyperbolic PDE has this form, has this shape. Okay, so merong spatial component at saka temporal component. Ang spatial component ay derivative with respect to x, second derivative with respect to x, at yung temporal component ay second derivative din with respect to time. So at this point siguro makikita nyo rin yung differences ng tatlo. So if you recall, meron tayong elliptic, meron tayong parabolic, and then meron ngayon ang i-discuss natin ay hyperbolic. So ang isang basic difference between the three ay sa elliptic, meron puro spatial components lang yung present, so walang temporal. Second derivatives lahat ng spatial components na yun. Sa parabolic, meron tayong spatial component na second derivative at temporal component na first derivative. Tapos, dito ngayon sa hyperbolic, makikita nyo na meron tayong spatial component na second derivative at temporal component na second derivative. Now, tulad din sa previous na types ng PDEs, may range yung spatial component. In this case, ang range natin is 0 to x sub f. At meron ding duration from time t equals to 0 to the total duration of capital T. And para ma-solve natin itong partial differential equation na ito, kailangan din natin ng initial conditions corresponding to the temporal component at boundary conditions corresponding to the spatial component. So, dito makikita natin yung boundary conditions. Ito ay boundary condition at x equals 0. At ito naman yung boundary conditions at x equals x sub f. Okay, given respectively as b naught of t at saka b sub xf of t. Yung initial conditions naman natin is given by u of x na 0, which is equal to I naught x. So ito yung ating equation for the initial condition. At yung second na initial condition is actually a first derivative with respect to time at t equals 0. Okay, tapos yung expression is given by I naught prime of x. Okay, so sa spatial component kasi, meron tayong limits, di ba? X equals 0, tsaka x equals x sub f. Pero sa temporal component, hindi natin alam kung ano yung mangyayari at t equals capital T dun sa end na time. Kasi nga, ang nangyayari dito is, ang isosolve natin dito is yung evolution from t equals 0 and then from each duration, kukunin natin yung bawat wave function na u. So, ang kailangan natin na pangalawang initial condition dito ay yung first derivative with respect to time. So, kaya ganito yung forms nung initial conditions. Okay, isang Dirichlet, kung natatandaan ninyo, at isang Newman na initial condition. Okay? Now, similar dun sa approach natin sa previous na types ng PDE, okay, ang gagawin natin dito sa second derivatives na ito ay gagamitan natin ng tawag dito, 3-point central difference. Okay? Approximation. Okay, so i-replace natin itong mga second derivatives na ito, okay, with these numerical derivatives. Okay? Again, ang superscript corresponds to time. Okay? And dito sa left-hand side, since ang pinapalitan natin dito ay, or kinukuha na natin derivative dito ay spatial component. So yung subscript, yung nagbabago. Okay? Now, dito naman sa right-hand side, since temporal component ito, yung superscripts naman yung nagbabago. Okay, so yung superscripts yung nag-evolve. Ang delta x ay yung sections, okay? So yung 0 to x of f ay di-divide natin into m sections such that each section delta x is equal to x of f, the total, ito yung maximum na value ng range divided by the number of sections. Okay. Now, yung duration delta t naman ay equal dun sa total time divided by n durations. Okay. So, pwede natin ngayon i-solve or i-rewrite itong equation na ito in terms of this. Okay? Kasi ang idea dito is alam natin yung time, initial time, and then gusto natin malaman yung next. So gusto natin makuha is essentially yung next na time step. So kaya ang sinasolve natin is u super k plus 1. Okay, so we are going to rewrite this equation in terms of u super k plus 1, k sub I. Okay, pag ginawa natin yan, ito yung makukuha natin na equation where itong r na ito ay constants which are equal to a times yung duration squared divided by yung section squared. Now, merong konting complication dito at yung complication will arise from this term specifically. Okay, bakit? Kasi if we start with k equals 0, so yun yung initial time. Okay? So ibig sabihin, ito 0, ito 0. Okay, at ito, meron tayong u super 1 sub I. Tapos dito meron tayong u super 0. At meron tayong u super minus 1. Okay? Now remember, ang initial time natin is k equals 0. Okay? Yan yung initial conditions. Tapos ang hinahanap natin is yung next na time step. Now, ang interpretation natin dito, since k equals 0, ito ay u super minus 1. This is the time step before the initial condition. So this is going back to the past, so to speak. Okay, by one duration. Okay, kaya makikita nyo rito, u super minus 1 sub I is the same as u of x sub I at the time duration of negative delta t. So bumalik siya by delta t. Okay, bumalik siya to the past by delta t. Ang problem dito is hindi natin alam kung ano yung value nito kasi ito nga, may initial condition tayo. Ang initial condition natin is u super 0. Diba? So, paano natin isi-solve yung problem na yan? So, ang gagawin natin is gagamitin natin ang tawag dito, derivative sa central difference dun sa second na initial condition. Remember, if you recall, yung second na initial condition is given by this expression. So, kukunin natin yung numerical equivalent nitong expression na ito. At ganito natin siya isusulat. U super I sub 1 minus U super minus 1 sub I. Okay, U super I sub 1 minus U super minus 1 sub I divided by 2 delta T. Okay, equals sa I prime not of X sub I. Okay, so yung second na initial condition ay nire-write natin in numerical form. Now we can solve for this. Okay, this is essentially U sub I minus 2 delta T times I naught prime X sub I. At ilalagay natin yan doon. When we do that, okay, we end up with this equation. Okay, so ito yung ating U sub I, itong U sub I minus super I, U sub I super minus 1 will be replaced by this. Okay, galing dito. Okay, and pag sinolve natin ito at saka ito, pinagsama natin yan, dalawa na yan. So, ililipat natin yan dun sa kabila. Di ba? We'll end up with this final equation. Equation 9.3.6. Okay? So, kung titignan ninyo, dito, ang sinosolve natin is yung wave function at the next time step using yung wave function at the current at the initial condition, wave function at the initial condition, wave function at the initial condition, and yung isang boundary initial condition. Okay? So, ito ngayon yung ating working equation. Yan yung igagamitin natin sa MATLAB. Iko-code natin sa MATLAB. Now, what about stability? So, we have this expression R equals A delta T squared over delta X squared. At para maging stable yung system, dapat yung R is less than or equal to 1. Okay? And since ang R is inversely proportional sa delta X squared, so the smaller this is, the larger this becomes. The smaller delta X is, the larger R becomes. Na kung titignan natin dito, ang maximum value ng R is 1, then, ang gagawin na lang natin is select natin yung value ng R to be equal to 1. Okay, yun yung reasonable na selection. Okay, so by doing that, we can select the values of delta T and delta X such that pag ginamit natin ito equation na to, magiging equal siya sa 1. So we want that kind of tawag dito, those kinds of values. Okay. So yun na yung one-dimensional wave equation, bali one-dimensional hyperbolic partial differential equation. Now, consider natin itong example na ito. So in this example, yung A natin dito is equal to 1. Okay, so this is the same exact equation. Now, yung range is, ang X ranges from 0 to 2. Okay, although, mamaya makikita ninyo, actually, hindi lang mamaya, dito sa boundary conditions, kung titignan ninyo, ang nakalagay dito is X equals 1. And sa code, makikita nyo rin na ang upper boundary niya is X equals 1. So, I suppose ito ay typo error. So, 0 to 1 lang dapat ang range ng X. Okay. Now, may nakalagay dito na Y na hindi ko alam kung bakit nakalagay dyan kasi obviously this is just one dimension. So, ignore na lang natin yung part na ito. But, okay, meron din tayong T dito na ang range ng T natin is from 0 to 2. So, yung ating initial conditions ay, so at U for all values of X, at T equals 0, equal dapat yun sa X times 1 minus X. Now, yung first derivative, okay, ng U with respect to T is equal to 0. Okay, at T equals 0. Now, ang boundary condition natin ay U at X equals 0 for any time T is equal to 0, and U at X equals 1 for any time T ay equal to 0. Okay, so basically lahat ng boundary tsaka initial conditions ay 0 except for this initial condition, which will be much easier to implement. Okay, so ito yung code, okay, but we're going to switch to MATLAB, okay, para mas makita nyo kung anong nangyayari. Okay, let's see. Ang gagawin ko is papakita ko both screens. So, ganito yung mangyayari. Okay. Gusto ko makita ko anong nakikita ninyo. Okay, so ito yung nakikita. Okay. Okay, so in this case, tignan natin ngayon. Ito yung code for the whole tawag dito, program for the solution of this differential equation. Itong differential equation na ito. Okay? So first, alam natin ang A equals 1. So ito 'yon. Second, we have these initial conditions. So ito yung unang initial condition. Ito yung nakalagay dyan. Okay. Ito yung pangalawang initial condition. Ito yung nakalagay dito. Okay. Ito naman yung unang boundary condition. Ito yung nakalagay dito. Okay. At ito yung nakalagay para sa pangalawang boundary condition corresponding to this equation. Okay. So, tulad ng sinabi natin, yung upper range niya is 1. This is divided into 20 sections. Okay, ang maximum time is t equals 2 units. At yung duration is obtained by dividing the maximum time by 50 durations. Okay, 50 time steps. Okay, ito yung mga given values. Ipapasok natin lahat yan dito sa ating function, sa function na ginawa. Okay, na ang pangalan ay wave, tapos ito yung kanyang mga parameters na pinasa. Okay, para dun sa function na ito. Ang output ng function na ito ay yung solution u, at yung dalawang independent variables. Okay, so kailangan natin to para mag-graph natin yan. And then this is just the labels. And ang ginagawa nito, kung napapansin nyo, naka-pause siya by 0.2 seconds. So ang ginagawa nito is animation. Okay, kung anong nangyayari dun sa wave, dun sa system. Okay, as a function of time. Okay, now tignan natin yung function muna na wave bago tayo tuloy. Bago natin i-click yung solve na button. Okay, now isa-isahin ulit natin to. So delta x, okay, itong delta x na to is equal to xf over m. So ito yung dx equals xf over m. Okay, yung x ay nagre-range from 0 to m. Okay, and then nalala nyo ito i-transpose divided by delta x. So ito yung buong value ng x. And then delta t is just capital T over n, and then ito yung lahat ng values ng t. Okay? So, ang ginagawa nito is para sa lahat, okay, for all values of x, ito yung initial or boundary condition. Okay? Sorry, initial condition, it, initial condition is it, not x. Okay? So, for all values of x, ito yung initial condition. Okay? And ito naman, for all values of t, ito yung initial, tawag dito, boundary condition at x equals 0, at ito naman yung boundary condition at x equals xf. Okay, so for all values of t. Ito solves for r, which is given by this. Okay, we also have r1 over, which is equal to just r over r2. Dito natin yan magagamit mamaya sa equation 9.3.6. So ito lang yan, basically. Yan. Okay, and then r2, okay, is just 2 times 1 minus r. So ito yung equation na yan. Okay, 1 minus r and then divided by 2. Okay, so ang u naman na to ngayon, yung equation, ang u na to is essentially ito yung equation 9.3.6. Pero kung papansin niyo, ang kinukuha lang dito is yung second na time, tawag dito na time slot. Okay, kasi alam natin initial conditions, di ba? Initial condition is given by this, di ba? T equals or K equals 1. Okay, excuse. Tapos, ang sinasolve natin ngayon dito is yung K equals 2. Okay, bakit K equals 2 lang? Kasi nga, sa K equals 2 lang, meron itong part na ito. Okay, for K equals 3, wala na yan, di ba? Dahil solvable na yung equation kasi itong part na ito ay known na. Okay, known na yan na quantity. Okay, so gagawin lang natin to for the next time step. At pag nakuha na natin yan, sa start na natin yung loop from the third time step hanggang dun sa huling time step. Okay, remember, n plus 1 to kasi meron tayong n duration, pero meron tayong n plus 1 na time steps. Okay? So, basically, yan yung ginagawa ng differential equation na ito. So, straightforward and simple. Okay, so, try natin ito ngayong i-solve. So, click natin itong run. Okay, i-focus tayo ngayon dun sa MATLAB. Okay, so i-run natin itong section na ito. Okay, so ito yung wave function. Okay, ang wave function dito is just this. Okay, remember ito yung x. At ito ay yung t. So ito yung evolution niya as a function of time. So ito yung first na time step, and then ito yung second na time step, and so on and so forth. So yan ang nangyayari sa kanya as a function of time. Now, if we take a look at x lang, okay, so dito natin siya makikita, ganito yung itsura ng wave function. Okay, so ganyan yung kanyang, ganyan yung naging solution niya. So, again, dyan siya sa simula, and then lumiliit yung amplitude niya, and then at some point, mag-invert yung amplitude, so on and so forth, and then babalik siya dun sa original niya na shape. Okay, so yan yung nangyayari dito sa tawag dito solution na ito. Okay. Now, let's consider the case. Okay. Na two-dimensional na wave function. Now, paano natin gagawin yun pag two-dimensional? Pag two-dimensional hyperbolic PDE, ang itsura ng ating wave function ngayon ay ito na. So, ano nadagdag dito? Ang nadagdag lang dito is this. Okay. Then, of course, magdadagdag tayo ng range. Okay. Ang range ng y is 0 to y sub f. Of course, magdadagdag din tayo ng boundary conditions corresponding to u at y equals 0 at saka u at y equals yf. Okay, so ito yung nagdagdag na boundary conditions. Pero yung boundary conditions for x ay pareho lang at yung boundary at yung initial conditions for time ay pareho lang din. Now, itong part na to ng differential equation na dagdag is also approximated by 3-point central difference. Okay? So, pareho, walang difference sa ginawa natin before, except na ito nga, nadagdag lang yung part na yan. And of course, nagbago-bago ng konti yung subscripts. Yung superscripts are still the same. And of course, dinagdag din natin itong delta y. Ang delta y is just y sub f over n sub y. Okay? Dapat m yata to para mas nagko-correspond dun sa spatial na component. Okay. Okay, which leads to this expression. Okay, so ang ginagawa natin dito, solve natin yung next na time step. Okay, okay, gamit yung current na time step. So tulad din sa tawag dito sa one-dimensional, at the second time step, meron tayo nitong tawag dito, wave function na nagre-require ng value niya before the initial condition. Okay? Na hindi natin alam. Okay? So, again, ang gagamitin natin is yung second na initial condition, i-replace natin siya with the numerical function. Okay, and then we solve for this, replace it here, okay, para makuha itong tawag dito, para makuha itong expression na ito. Okay, may 2 dito supposedly, pero nire-write na lahat ito. Okay, para mas mabilis na yung pag-present ng solution. Okay, now in this case, ito na yung magiging equation natin for stability. Okay. And makikita natin na nadagdagan itong term na ito. Okay, delta y squared dito. Okay, tapos saan nanggaling yung 4? Okay, nanggaling yung 4 dahil meron na tayong 2 terms dito. Okay, 2 terms. Ito kasi 2 dito at saka dyan. Okay, so dyan nanggaling yung 4 na yan. Okay. So let's consider this example. A two-dimensional wave, okay, over a square membrane. Now, in this case, hindi na natin makikita yung tawag dito, ang i-graph na natin dito is spatial components lang. Okay? Tapos, yung bawat spatial component, tawag dito, bawat spatial component ay merong time, may corresponding rin na time. So, ang makikita nyo dito is spatial component for the initial time, okay, yung spatial component for the next time step, spatial component for the third time step, and so on and so forth. So, makikita nyo na yung buong, ang tawag dito is membrane, kung paano siya nagbabago over time. In this example, ginamit niya na range for x ay 0 to 2, for y is also 0 to 2, and for t, it's also 0 to 2. Okay, medyo consistent na siya dito ngayon. So, dito ang x is 0 to 2, so yan yung ating boundary conditions. Ang y is also 0 to 2, yan yung pangalawang boundary condition. Yung unang initial condition has this form, so sinusoidal na yung yung function, okay, at the initial condition. And then yung first derivative is 0 for t equals 0. Okay, now if we use yung values na gagamitin mamaya for dito ang pinakita dito is n equals 20, tapos m sub x equals 20, m sub y equals 20. Pag yan yung mga ginamit natin, ang makukuha natin r is 1/2, which is clearly less than 1. So ibig sabihin stable yung system. So ibig sabihin din nito, kahit na anong piliin natin na n, m sub x, tsaka m sub y, yung system will always be stable dahil dito sa sum na ito, delta x plus delta y squared, na parating mas malaki kumpara dito sa delta t squared. Okay, so ito yung wave function, makikita nyo sa book, at ito yung basically yung solution, okay, expressed in tawag dito code. So, tignan natin ngayon yan sa MATLAB. Okay, so ito. Oops. New share. No. Okay, so nakikita nyo na itong both screens. Okay, ngayon, dito tayo sa two-dimensional hyperbolic PDE. Ito ngayon yung solution. Okay, so again, balikan lang natin itong boundary conditions tsaka initial conditions. So ito yung initial condition corresponding to this. Ito yung pangalawang initial condition, okay, corresponding to this. Ito yung unang tawag dito, bxyt. So, ang bxyt, okay, lahat, okay. So, ginamit niya na for all. Okay, so lahat ng ito is exactly expressed by this. Okay. So, makikita nyo naman na pinasok nyo na yung bxyt dito. Okay, at pag ginamit na siya doon, i-call na lang yung bxyt. Okay, dyan. Okay, so yung a dito is 1/4, okay, as given by this, makikita nyo dito sa example. Saan ba yun? A is 1/4, so a is equal to 0.25. Okay, tapos yung range is 0 to 2 for x, tsaka 0 to 2 for y. Yung t, ay maximum value niya ay 2. Tapos dito ang section, number of sections along the x ay 40, number of sections along the y ay 40, at yung number of duration along over time is also was also set to 40. Tapos lahat ng mga variables na ito ay pinas dito sa wave function 2 na magsasolve ng two-dimensional wave equation. Ang output ng wave function na ito ay yung amplitude and then yung values ng tatlong independent na variables. Okay, so ito yung wave function, yung function natin that will solve the 2D wave equation. Okay, so straightforward lang naman ito. Ito yung dx, then yung x, ito yung dy, at saka yung y. Okay, ito yung dt, tsaka yung t. Okay, na ginawa na rin, na pinakita na rin natin before. Initialization lang ito. Okay, para mag-allocate ng space. Para sa variables na ito. This initializes yung time, yung initial conditions for all values of x. This solves for the numerator ng r. Okay. Numerator ng r. So ito. Okay. Delta t squared for a. Yan. Ito yung rx. A dt2 dx squared. So bali dito yan. Yan. Ito naman yung ry. A dt2. Okay. Yan. Tapos, Rx1 is this. Yan. Okay, 1, sorry, ito pala. 1 minus Rx minus Ry, Rx2 is Rx1 minus times 2. So, basically, ito. Okay, tapos, initial value niya din to. Okay, tapos, dito pinapalitan nyo na yung time. So, bali, yung time t, okay, for each k. So, halimbawa, for k equals 0, then time na to is 0. And then for k equals 1, then this corresponds to dt. For k equals 2, this corresponds to 2 dt, and so on and so forth. At yun yung i-replace dito sa mga naka-highlight na yan. Okay? Yan. Sa mga naka-highlight. This solves for the boundary conditions. This is basically, ito na yung ating working equation natin. Okay. Again, magsa-start muna siya sa k equals 0. Okay. Alam natin yung value or initial condition at k equals 0. So, solve niya muna yung k equals 1. And then, pag nagawa niya na yun, kukunin niya na yung succeeding time steps. Tapos, nilalagay niya lang yung information ng wave function dito sa U2 tsaka sa U1, okay, para magamit siya dito. Okay. Yan, dito sa taas. Tapos, and then ito i-graph niya na for each time step. Okay. So, pag sinolve natin yan ngayon, okay, dito pala. Okay, ganito yung magiging itsura. Okay, nasan siya? Oops, yeah, okay. Nangyari dito. Hindi natin nakita na. Iulitin natin. Wait. Okay. So, ulitin natin ito. Run section. Ah. Bakit niya hindi pinapakita yung at each time. Okay, let's see. Okay, let's do one more thing. Hintayin tayong konti. Medyo weird na hindi niyo pinapakita lahat. Ayun, okay. Ngayon nag-work na. Okay, so nakikita natin na kung ano nangyayari dun sa membrane for each time step. So bagalan natin ito ng konti. Okay. So ganyan yung nangyayari sa kanya at each time step. Okay? So makikita nyo na maangat baba lang tong sections ng membrane. Okay, at yan yung solution ng ating wave function given by this. Okay? Okay. So, tulad nung ginawa natin before, i-upload ko ulit ito sa VLE. Okay, para makita nyo kung paano ito nag-work. Okay, at pwede nyo paglaruan, okay, kung gusto niyo. At of course, pwede nyo ring, dapat nyo lang din pag-aralan, tignan nyo kung paano siya nag-work. Tapos, on Thursday, magmi-meet tayo online, okay, para ipakita sa inyo kung paano gamitin yung PDE modeler at i-discuss din sa inyo yung machine problem 6 kung anong kailangan yung gawin doon. Okay? So, thank you for watching and kita-kita tayo sa Thursday.